Hello, and welcome back to another video with It's Dr. Dan. And today we're going to be looking at conjugate acids and bases. Now, what this is all about is that when you have acids and bases reacting together, they can reach chemical equilibrium, which what that is a concept that we will focus in other videos. But the whole idea is that whenever you have, let's say, weak acids or weak bases, which are weak electrolytes, they generally do not fully dissociate whenever you put them in solution, so they don't fall apart as easily. Now, with those, the whole idea is that their reactions are considered reversible, meaning that the reaction can go backwards or it can turn back from products to reactants. So, whenever we have something in equilibrium, this is when we say essentially that the products and the reactants are reacting at the same rate. So we have a forward reaction, and when we also have a backwards reaction happening at the same time, which is a little crazy to think about. That it can get even more complicated. Now, whenever we have essentially products that can possibly turn back into reactants, right? So going backwards, we can actually use a equilibrium constant to describe it, especially when we're talking about solutions and gases. So what this constant is called a K value. And what it does is it takes the concentration of the products and then divides it by the concentration of the reactants. So it's molarity for the products on top and then the molarity of the reactants on the bottom. And it's a ratio. So what it tells you is that, okay, if there's more products, then the reaction is going to be a big K value. It's going to go forward. And if there's more reactants, it's going to be a small K value, meaning the reaction is going to go backwards as a result. So which way is that reaction going to go? Now, from there, whenever we're indicating these different types of reactions, the first part is the forward reaction. So what you're used to is that the forward reaction is always indicated by an arrow that's going from left to right. So it's always going from left to right. Now, a reverse arrow is the opposite. So it's going from right to left. So if you have it going from right to left, that's indicating the reverse. So now, if the fact that we have this equilibrium process and we have both forward and backwards, so what we're going to do is we're going to combine their powers together and we're going to make an equilibrium arrow as a result. So you'll see this double arrow that's going to be placed in a lot of reactions that have weak electrolytes. And that's telling you that the reaction goes forward and back. So does that mean you got to do anything else in terms of balancing or anything in terms of reactions? No. All it's telling you is that the backwards reaction is possible. It's the same process that you were using before, but it's giving you another piece of information that the reaction has a tendency to mainly stay as reactants or mainly stay as products, right? Depending on the conditions of the reaction. So if we were to try to, let's say, label what we refer to as acid and base pairs, how exactly can we do that? Well, the first thing is labeling what is considered an acid. So here I have the letters HA to represent our acid because acids donate protons. So what's going to happen is this HA is going to donate its proton to the water molecule here, which means that this is considered the base. So when we have our final products, we are going to have A minus as one answer because HA lost its proton. And then we're going to have H3O plus as the other answer. Now, what this whole thing about conjugate acids and bases is about is that the backwards reaction also has acids and bases in it as well. There's a pair of them, meaning that you have an acid base pair on the left-hand side of the reaction all the way on over here. And you also have an acid base pair on the product side too. So if we were to look at this, what can donate a proton between A minus and H3O plus? Which one has hydrogens to give? And you're going to see that, oh, well, H3O plus can give a hydrogen. So what that's going to happen is this one is going to donate its H plus to the A minus, making HA, going back. So as you can see, this one is related to the molecule on the other side. So what we can do here is we can label H3O plus as an acid and A minus as a base. Now, because these are on the product side of the reaction, this is what we refer to as a conjugate acid and a conjugate base. So let's move those names down a little bit, and now we're going to add the word conjugate. So now that we labeled that, what we can now see is that there are acids and bases on the left and the right. Now, the thing about this is when we're looking at this, that there are going to be two pairs of acids and bases. So not only are there some on the left and the right, but there's also between the two sides of the reaction too. What you are looking for is essentially common anions or common cations in these equations. So for example, one of them is A minus, right? So that, as you can see, there's an A on the conjugate base. There's also an A on the left-hand side in HA. So these two together are referred to as a conjugate acid-base pair because they have the same common ion in each equation. Now, when it comes to the other two, which is the one with water, well, what's the common piece between H2O and H3O plus is water is the common part of both of them, right? The only difference is one H plus. So when you're looking for a conjugate acid-base pair, you're looking for the difference of a single hydrogen between the two pairs. So is there a hydrogen difference? So both of the ones I labeled here in that yellow and that peach color, these are referred to as conjugate acid-base pairs. Let's look at some more examples of this. Hydrogen. So whether it's present or it's absent with the difference of a proton, that means it was transferred. So whenever we're looking at these pairs, right, if we look at the one here, which is the same we showed before, if I look at HA and A minus, they differ by a single proton. So this is one conjugate acid-base pair. On the other hand, we have water and H3O plus, which also differ by a single proton. This is the second conjugate acid-base pair. Every single reaction has a pair. Let's go and look at more. So given the following reaction, determine its conjugate acid-base pair in the reaction. So what we are looking for is things that have a difference of a single proton. And we also want to be able to label if it's an acid or a base in the reaction as well. So if we look, what can we see in terms of the products and the reactants? We see ammonia is reacting with water to create NH4 plus and hydroxide. So the thing that we want to look at, if I look at, let's say, water, we can say that it donated an H plus to ammonia to make ammonium, right? So we see the difference on the side here. So when we label these, we can see water is behaving like an acid, and then ammonia is behaving like a base. So its pairs in this case is that H2O is paired with hydroxide, right? They differ by a single hydrogen, right? OH minus is missing one proton. So what does that make it? Well, there has to be an acid-base pair. So hydroxide is going to be the conjugate base. So if you ever see CONJ as an abbreviation, that's referring to conjugate. So what that means now is that if this is the conjugate base, then the other molecule must be the conjugate acid, which therefore will be paired with ammonia. So these are the two. Now to check our work, we can look at the reversible side of the reaction and see, does it agree? So in that case, ammonium should donate its proton to hydroxide to make water, right? And then you can see that that matches on the left-hand side. So what we always have to do is we have to identify what the donor and acceptor are in our steps, then identify the pairs in all these different reactions. Let's take a look at another example of this. Given the following reaction, determine its conjugate acid-base pair. So the first thing we got to do is identify the donor and the acceptor of the protons. So one thing that we can see is where is our acid? And we can see that H2PO4 is donating its proton to NH3 in this case. So now when that happens, how we can do to label that is that means that H2PO4 is our acid and NH3 is the base. Now on the opposite side of the reaction, what's being the donor? Well, what we can see is that H4 plus is donating its proton to HPO4. So in this case, we have our conjugate acid and our conjugate base. So conjugate acid and then conjugate base. So now we got to pair up the different types of acid-base pairs. Let's erase these arrows. So on the left-hand side, I will pair my acid with my conjugate base. Oops. And then on the right side, I will pair up my base and my conjugate acid. And those are our two pairs. Let's take a look at some other examples. So let's say I want to predict one from start to finish. How would I do this? So right here we have HClO and CH3NH2. So the first thing we got to do is identify the acid. The acid always generally has a H in the front of the reaction. So what this is going to be doing is it's going to be donating its hydrogen to the other species. So when that happens, well, what's going to be left is we're going to have ClO minus, being that's going to differ by one proton. And then the other one is going to be CH3 NH3 plus. So we have our acid-base relationship. So that means on the other side, right, NH3 is going to donate its proton the other way, right? So we can label everything. So we have our acid, which is HClO4. We have our base, which is CH3NH2. And then we have our base and acid as well on the other side, which are our conjugates. So let's add up all those labels. Now that we labeled them, what we can now show is our little lines to kind of represent the different pairs. So we have our acid partnered with our base, and then we'll have our base partnered with its conjugate acid. And these are the different pairs in this reaction. Let's look at another example. So a very common question that you will receive on exams, homework, or even on finals is what is the conjugate acid or base of the following reaction? Meaning that you have to be able to identify if it's an acid or base and then determine what would it turn into. So for the first one, I have HF, which means that this is a very common weak acid. So when that dissociates in water, it's going to essentially make H plus and F minus, right? So F minus would be its conjugate base in this type of situation. So what formula differs by a single proton? And we can't become more positive. We can always become more negative when we're looking at those conjugate bases. So that is an example of one. On this next one, this one looks a little bit different, and that's because I wrote it purposely like an organic acid. This is the acetate ion connected to a hydrogen, so it's acetic acid or vinegar. So one way that this can be seen is the following CH3COOH, or it can also be shown as H2C2H3O2. So there's another way to represent that. So that way the hydrogen's in the front. It depends on kind of what you're looking at. So the acidic hydrogen is the one that's all the way on the end over here, whereas the acidic hydrogen is written on the left-hand side. So we have essentially the Chem 3A version on the bottom and then the Chem 3B or organic version on top. So when this breaks down, we're going to have our acetate ion is going to be one structure, and then you're going to have your hydrogen ion. So what we will have is we have our acid, and then our conjugate base on the other side. So that is our pair. Now the next one, well, it's NO3 minus, and there's no hydrogen to take from it. So what does that mean? Well, if it were, let's say, to react with water, for example, it would end up receiving one of those hydrogens. So if you want, you can always kind of see how would it actually react with the water. And if we were to do that, well, we would end up having HNO3 and OH minus as the other product. So if we were to try to label that, this would be the base, and then this would be your conjugate acid in this reaction. They differ by one single hydrogen. Now, sometimes they can be a little bit different. You could go potentially one way or the other. So HPO42 minus, you can actually go either left or right, depending on how you look at it. So with this one, I can either receive a proton or I can take one away. So being that it's negative, it could accept more protons. So either we can make PO4 3 minus, which is the phosphate ion, or I can make H2PO4 just minus to receive one more proton. And if you really want to think about it, this can even go another step where it can receive a extra one to make phosphoric acid. So it all depends on how many charges does it have, how many protons are available. So with this original question, what we kind of have here, depending on which direction you go, could label it as the acid or base with all these different pieces. Okay. So this has been the whole idea of conjugate acids and base pairs. So let's kind of summarize it real quick. So the whole idea of it was that essentially whenever it comes to these reactions, you're looking for the acid and base between the left and the right that differ by the presence of a single hydrogen or proton inside of the equation. If you find that proton difference, you can label the acid on the left-hand side or the right-hand side. This is something it's easy to kind of make mistakes. So try to practice it, write it on an index card for that definition so that way you can remember it for later. All right. Thank you so much for listening. I hope this video helped. If it didn't make sense, please let me know by sending me a message or sending me an email or commenting below on the video. Whatever you need to help you pass chemistry, please reach out. If this is your first time here, please hit that like and subscribe button. And thank you so much for supporting the channel and watching the video. I hope you all have a wonderful day, and I'll see you all later. Bye now.